Software development for real-time embedded systems.
Project 3.
Hello, I'm Daniel Neal with partner Brad Finnegan, and this is the demonstration for Project 3, Measure and Transmit Fan Speed and Thrust. In this project, we've designed a system to drive a brushless fan motor with pulse width modulation and determine its speed in rotations per minute dynamically with an IR emitter and receiver circuit. First things first, let's cover the hardware setup.
First off, we have our Arduino Uno. Next, we have an external power supply hooked onto the breadboard. Up next is the IR phototransistor here, connected to a 10K ohm resistor and feeding its output to the analog pin A0 on the Uno. And this clear LED is the IR LED. It's connected to a 150 ohm resistor. Finally, the 3 to 6 volt DC motor that is driving our propeller. So that we don't damage the Uno sends the inputs and power to an L293 Delta chip, which then controls the motor. We had to paint our propeller because the blades were initially semi-transparent, which wouldn't have been very helpful for this project.
Now on to software. Our design involves a round-robin with interrupt approach, using two distinct interrupt service routines, with the main loop checking against two conditional flags corresponding to either ISR action. And if neither is high, it will just continue polling indefinitely. Up at the top, we have global definitions, setting the pin numbers for the photodiode and for the fan motor, the number of fan blades in case a replacement is made, the baseline PWM value to overcome friction at startup, which likely could be lower when we're using the battery, but this is what we're running with. The upper and lower bounds to define IR receipt and blockage for our simple state machine. A buffer defining the number of continuous readings at a certain threshold to address debouncing and remove any erratic readings, as well as the periodicity of PWM modifications catered for this demo. In this case, it changes every 10 seconds. Here's the enum for our mentioned simple state machine, on or off. A litany of global variables, and the setup. We turn off interrupts, initialize our globals, set our pins to output, begin our serial connection, and the first interrupt is configured, this one being timer 1 set at a 1 Hz interval. We use this for Project 2, it's old hat by now. Our new interrupt is the Arduino analog to digital converter. The ADC is configured to run in free run mode, which means that it triggers an interrupt after every single conversion. This clocks in at around 9600 conversions per second on the Arduino Uno, and we are ensuring that our photodiode analog input is the only one entering the multiplexer that will trigger this ISR. Looking back at the ISRs I showed briefly earlier, the ADC interrupt routine simply retrieves the most recently stored ADC digital value directly from its two registers. And documentation tells us that it is actually important to read ADC-L before ADC-H. We put this combined 16-bit value into the last ADC integer, and then simply raise the service photodiode flag high. As for the 1 Hz timer, all we do is raise a flag for task code to be enabled. So now down in our main loop, as mentioned, we're simply polling for these conditional flags. And I'll start with the ADC conditional. Obviously, we lower the flag so that it can run again in the future, and we temporarily disable the interrupts so that we can grab that shared data that saved our ADC measurement into a local integer. Afterward, we enter this very simple pseudo state machine. It's only two states, off and on, that toggle between one another when conditions are met. These conditions correspond to the ADC value staying above or below the associated threshold for a number of continuous reads, the value of which was assigned in this PD state buff constant from the global definitions. When both of these conditions are met, the state toggles to the next one, we reset the buffer count to 0, and we increment this blink count variable. And as you can see below, it's a symmetrical process. The other state does the same thing, but with the IR high bound threshold, and the ADC value having to keep above it rather than below the low bound. The buffer is meant to combat debouncing and or erratic measurements, but our testing showed that the setup is relatively stable without any buffer. Removing it would increase the fidelity of the RPM calculation, but at 9600 samples per second, we have more than enough leeway in the demo to enforce a buffer without underestimating the RPM. Now returning to our timer-based task code, we're also grabbing the ADC value after disabling the interrupts, but this is purely to have a variable to send to the serial port. What is important is that blink count variable I showed earlier. We use the number of blinks, which correspond to the IR suddenly turning on and turning off, to calculate the RPM values from the last second. And that's actually right down here, with the RPM corresponding to blink count times 60 seconds divided by 2 blinks per blade because it blinks when it goes on and off, and divided by the number of fan blades, in our case it's 3. However, we're also tracking the actual RPM of the last 60 seconds, using this tally that increments the blink counts every 1 second, and ultimately corresponds to our blink history array, which consists of 60 integers that cycle through based on the current seconds since start, and roll over appropriately. After finding these values, the task code reports system information over the serial output in CSV format for the user to evaluate. This includes the current time since start, number of blinks in the last second, current PWM value, the RPM of the last second, and the RPM of the last minute. Finally, every PWM period, the PWM value increases by 16. If you recall, it starts at our PWM base, which is 175, and increases all the way to 255, the maximum PWM output value, before rolling back over to the base. And we accomplish this through an analog write to the fan enable pin. Earlier we set the 2 fan direction pins to high and low in order to make this go one way. Then we increment the time and we reset the blink counter so we can start fresh for the next second. And that's the long and the short of the relatively simple software design. Next up is the demo. Alright, first taking a look at our previous run to synchronize videos. Here is our makeshift setup, Reese's Pieces and all. We have our IR receiver photodiode, our fan sharpied over to make sure it's not semi-transparent, and our IR emitter. And it is aligned so that the fan blades will block the front of the receiver while it's running so that we can accurately count these blinks. And looking from the other side, those look delicious. And here's our wiring setup. In order to accurately get power where it needs to be, we have a D-volt battery supplying up to 6 volts to our fan. Now I will upload the code to the Arduino, or the Elegoo in this one. They're basically equivalent. We're starting our timer, and there's no power currently, so the fan's not moving. We're recording 0 RPM, and now we start the fan, and we are seeing a lot more rotations. As mentioned in the code, the PWM started at 175. It missed a lot of that startup because there was no power being driven, but it increments by 16 every 10 seconds until it hits 255, the maximum. Then it will roll over back to 175, and we'll see an appropriate drop in the current RPMs as we hit that. The fun aspect of this demonstration is that the PWM is in a loop. There are 6 different states from that 175 to 255, and each one is 10-second period. So we actually average out to a pretty constant RPM over the past 60 seconds once we get around to the 70-second mark after it's spun up and backfilled the zeros in the blink array. And I let it run through 2 full iterations, 2 minutes of these pulse width modulation shifts, until turning it off, and we can see that the blink counter goes down to 0 along with the RPM. And that is the core demo. Now here's a fun little addition without the fan running. The fan is not between the IR receiver and emitter, but this Sharpie sure is. And you'll be able to see as I frantically wiggle the Sharpie up and down, we will get blink counts and it will estimate an RPM value based on this, though it does think there are 3 blades still, so it's not quite accurate, but it does show the design works on slower moving objects as well. And here you see our results. The serial output CSV ports over quite cleanly. We have over 2 minutes of recordings, and these are directly from the demonstration just shown. This top figure shows our per second calculated RPM over time. The PWM increment steps are fairly clearly represented every 10 seconds, with a sizable RPM increase when enforcing the max 255 value before rolling over and dropping back down to our baseline. And we did receive 0 at the front and the back, so there were no erratic high signals being represented. And the bottom figure shows the per minute tallied RPM over time. There's an expected rise from around 10 to 70 seconds as the program backfills the 0 array, but once the fan has been running for 60 straight seconds, it maintains a fairly consistent RPM of 1320 to 1330. As mentioned, the results are stable because we tailored the demo to be a 1-minute loop. And that concludes our project demonstration video. Thank you for watching.